All right, let's jump straight into this explainer. We are decoding the find all permutations algorithmic problem today, and we're going to master the art of the state space tree. If you've ever felt, completely overwhelmed trying to mentally track how a computer explores every single possible combination of a dataset, well, you're in the exact right place. Today, we're making the invisible visible.
So the key word we really got to focus on for our problem today is all. We aren't just trying to find one single correct answer here or optimizing for just one quick path. No, we need a methodical, absolutely foolproof way to conduct an exhaustive search of an entire array. We need an algorithm that guarantees we generate each and every possible permutation, one at a time, without missing a single one, and, just as importantly, without repeating ourselves.
Okay, here is our roadmap for the explainer. 1. The permutation problem. 2. The backtracking intuition. 3. Visualizing the state tree. 4. The traversal process. And finally, 5. Time and space complexity.
Let's kick things off with part 1, the permutation problem. This is where we define our exact input.
The premise here is actually pretty straightforward. We're given an array of unique integers. For our specific exercise today, our characters are the numbers 4, 5, and 6. Our objective? To return every single possible arrangement of these numbers, in absolutely any order. So, for instance, an input array of 3 numbers is going to yield an output of 6 distinct permutations. But how does a computer actually, systematically, build this list from scratch?
That brings us right to part 2, the backtracking intuition. It is all about trial and error.
The algorithmic technique that naturally fits this whole requirement is called backtracking. Honestly, think of it literally like exploring a giant maze. You walk down a path until you hit a dead end, right? Then you retrace your steps just enough so you can find a new, unexplored corridor. As we build out our permutations, we're going to pick numbers one by one. And to make sure we don't accidentally reuse the same digit in a single arrangement, like we definitely don't want a 4, 4, 5, we'll cleverly use a hash set to keep a running tally of our used numbers.
Let's move to part 3, visualizing the state tree. This is where we visually map out the entire process. Let's actually figure out how to build just one permutation to start. Let's look at how we begin our initial descent. The root is just a totally empty permutation. First, we picked a number 4. So our current state is an array with just 4 in it, and our used hash set makes a little note that 4 is taken. Then, for the second position, we move down the tree and choose 5. Finally, we add 6. And since we've now used all the numbers from our input array, boom! We have successfully built our very first completed permutation candidate. But here's the catch. Having found one answer, we've effectively hit a dead end. We literally can't go any deeper. So to find the other permutations, we must backtrack. We reverse course by removing the most recently added number, which is the 6, from both our candidate array and our used hash set. This upward movement brings us right back up to the state of just having 4 and 5. Now we pause for a second and ask, are there any other numbers we can append to this array of 4 and 5? Well, looking at our input, 6 was literally the only remaining option, and we just explored that path. So we've got to backtrack once again. We remove the 5, moving our candidate array all the way back to just the number 4. Back at this higher junction, we ask that same exact question again. Are there any numbers other than 5 we can add to our 4 at this specific point? Yes, the number 6 is available. So we pivot. We speed right back down a totally new branch by choosing 6. Our state is now the array 4 and 6.
Continuing down this fresh path, we look for our final number. The only remaining unused number in our input is 5, right? So we add it to the 4 and 6, and just like that, we get our second successful permutation, 4, 6, 5. We found another complete arrangement simply by retracing our steps and making the next available choice. Super elegant.
And this perfectly illustrates the full state space tree in all its glory. It really shows how we repeat this exact momentum, descending, hitting a dead end, backtracking, and then pivoting across all possible branches. Every single time our partially completed candidate reaches the length of our input array, which we denote as n, it becomes a leaf node at the very bottom of this tree. For our specific input of 4, 5, 6, the tree maps out to exactly 6 leaf nodes, representing our 6 total permutations.
All right, part 4, the traversal process. Let's translate all this theory into actual code.
Translating this tree into an algorithm really just means setting up a traversal playbook. It is a repeating cycle of just 3 simple steps. Step 1, pick an unused number to add to your current permutation candidate and instantly mark it as used in your hash set. Step 2, make a recursive call, meaning the function actually calls itself, passing along this updated candidate so you can dive deeper into the branches. And step 3, once that recursive call finishes and returns, you backtrack. You do this by removing that exact last number from both your candidate and your hash set. You have to do this so the next loop iteration can cleanly try the next available number. And of course, whenever your candidate hits the target length, you save a copy straight to your output. This brings us to our final section, Part 5, Time and Space Complexity. Let's talk about the physical cost to the computer.
When we break down the complexity, we actually get this really fascinating split. Space complexity stays highly efficient at O of n. And why is that? Well, because the maximum depth of our recursion tree, like the absolute furthest down we ever travel at any one single moment, is simply the length of the input array, n. Our candidate array and our used hash set also only ever grow to a maximum size of n. But the time complexity? Well, that's a completely different beast entirely.
We land on this massive, almost startlingly large time complexity of O of n times n factorial. Let's quickly break down why it is so heavy. Starting from the root, we explore n candidates. For each of those, we explore n-1 candidates, then n-2, all the way down to 1. This math naturally generates a total of n factorial permutations. But remember our code logic. Every single time we reach a valid leaf node, we have to physically make a copy of that array to add it to our final output list. Making that copy takes O of n time. So, n factorial permutations multiplied by the O of n time to copy each one equals O of n times n factorial. It's expensive, for sure, but when the problem demands literally all permutations, it's just structurally unavoidable.
So, the absolutely crucial takeaway here is that mastering this tree traversal is a foundational skill for countless computer science problems. Once you can really visualize the descent, the backtracking, and the pivot, you can solve almost any combination puzzle out there. But I want to leave you with a quick question to test your new intuition. How would your algorithm and your state space tree have to change if our input array wasn't full of unique integers? Like, what if you were asked to find all permutations of the array 4, 4, 6? How do you prevent the tree from generating identical duplicate branches? Ponder that structural change, and until next time, keep exploring the branches.